Welcome to a concept review module on statistics. This is part two of a two-part statistics for geospatial technology concept module, and it's more advanced than part one. Hello, I'm Ann Johnson, Associate Director of the Geotech Center, which is a National Scientist Foundation grant. This is specifically geospatial statistics, so while it's based on classical statistic concepts, it really adds geography, the location, into these mathematics and analysis tools. So it's not just telling you how many mean, median, and mode for something, but also where that something occurs. So it is adjacent to, proximity to, connected to, and possibly with temporal relationships. This is part two. Part one of the statistic concept module reviews basic geospatial statistic terms and concepts, where this one will review more advanced definitions and descriptions. This part two statistics concept module will define terms used in more advanced geospatial statistics. It'll also review some of the advanced methods. It will describe too some of the techniques that are useful. Also included will be some ways to learn more about advanced geospatial statistics. This concept module covers topics that are usually included in upper division or graduate level courses. But what's occurring now is many software applications are including the ability to carry out these techniques by pushing a button or running a script. So these will at least introduce you to these terms, and you may want to go on and take a course to really get in-depth education. So some of these will be fairly brief explanations. Really the object is to move you from just pushing a button to understanding what the function is and why it's used. These are different terms: inference, probability, null hypothesis, weighted average, inverse distance weighting, spatial autocorrelation, significance, P and Z values, clustering and dispersion, RMSE, kriging, variograms, semi-variograms, and R software. Tobler's first law of geography states that everything is related to everything else, but near things are more related than distant things. Geospatial statistics can be used to see if this is true for specific features or entities and their attributes. It can be used to suggest or infer a relationship and actually provide some quantitative values that can support the probability and strength of the relationship. Why are advanced geospatial statistics useful? Often all data locations and attributes for an entire study population are just not available. One reason or another, think about if you're prospecting for gold, you probably can only do some sample of all your locations to really determine whether you want to continue. Same thing in healthcare or census data. You may not have all of the population, but if you can take part of the population and run statistics on it, you may be able to make inferences and draw conclusions using that sample population or models, rather than having to have access to the entire population. So statistics can be used to suggest the probability that the results from the study provide a reasonable outcome. Note the two terms here, inferences and probability. So we're talking about finding ways when you do not have all of the data available for a population and make assumptions or inferences on outcomes. Null hypothesis in spatial statistics is one technique used to determine whether the observed results of an analysis are significant. That is, do they really show clustering or dispersion of features or attributes, or are they just chance or random processes? So a null hypothesis can help evaluate significance or non-randomness using a normalized bell curve of all of the observed values. We're going to look at two values, the p-values and the z-values. P-values are probability that the result would not result from chance or random processes, and the z-values, really standard deviation, with different very high or very low values suggest it is also not due to a random process. This is that normalized bell curve, and you can see that there's significant levels for the p-values and critical values for your z-scores. And the bottom of it is color-coded and with p-values and z-values. P-values are the probability of a pattern created by some random process, stochastic process. A very small p-value is not likely to be random. So we can see on our bell curve here that p-values of 0.01 to 0.10 are significant. Same thing, 0.01, 0.05, 0.01 on the right side of the bell curve. C-values, if they're very low or very high, are also not likely to be random. A definition for a stochastic process in probability theory is a system of random variables with numerical values that change over time. Weighted average versus just average. Well, the average or mean value is just determined by adding all the values in a collection of data and dividing by the number of items or terms in that collection. In weighted average, we have some of the values in that collection are counted more heavily than other numbers in the collection. A little bit hard to understand, so we're going to do an example of that. Weighted average example, say you're going to calculate a grade in a course, and it's going to be based on a weighted value for different types of assignments, and then normalize it to 100% of points. So if we say homework is not terribly important, you get 10 points, but it only counts to 20% of your grade. Projects get 30 points, 30% of your grade. Class participation, while it's important, it only counts 10% of the grade. And of course, your final exam is very important, so it's weighted at 40%. So if a student earned these points on 10 on homework, 15 on project, 10 on class participation, and 30 on exams, and we add all those values up and divide by the number of points for their percent, we end up with a student grade of 65%. Not exactly passing in this instance. Inverse distance weighting, we're thinking of Tobler's first law where everything is related to everything else, but same things are more related than distant things. Inverse distance weighted assumes that close things are more alike than distant things. Thus, the values close to the predicted location have more weight than distant locations, which diminish as the distance increases. Weights are proportional to the inverse of the distance between the locations, and spatial autocorrelation is the underlying assumption. Use of Moran's I equations helps to compare the degree that one object is similar to other objects that are nearby using multiple dimensions over spatial extent. Spatial autocorrelation can be positive, where similar objects are clustered, or negative, where dissimilar objects are next to each other, or there can be no spatial autocorrelation. The equations below are the basis of this analysis and are beyond the scope of this review, but many software packages incorporate the use of Moran's I. For more information, there's some resources from the GIS Lounge and from ESRI's ArcGIS Pro tool of reference. From ESRI, the diffusion of an idea, a disease, or a trend over space and time is the idea, disease, or trend remaining isolated and concentrated, or spreading and becoming more diffuse. Again, there are tools within software packages that allow you to do this, so it is best to learn more about it. Clustering, though, where spatial autocorrelation with Moran's I, evaluation of the features and its attributes can be done to see if there is a dispersed or random or a cluster. A little illustration below shows dispersed greens and pinks of different colors. As you go to the right, we go from being truly dispersed or random to being clustered. Nearest neighbor, that's calculating the nearest neighbor based on the average distance from one feature to its neighbor. Again, on the left, we can see that they're really dispersed, random, and they become more and more clustered as we go to the right. Root mean square, RMS, and root mean square error. Again, these are equations that you should become familiar with. It's another button on many of the software packages, and we're looking at the square root of the number of entities in your data set, and each of the entities are squared, added together, and then divided by the number of entities. Root mean square provides a way to measure that difference between what is the predicted value from your equations to what you actually observed, or the O for a number of values. Here, weather gives you a good example. So you can predict the weather and you get a prediction temperature, but then you can compare it to the actual temperatures and see what your error was. Often there are gaps in data, so we can't collect data for a complete population. Maybe it's too costly or difficult or deny access. Go back to the gold prospectors. They may have to determine if a site is worth mining by using data from a limited number of borehole samples. There may be gaps in coverage, making it hard to know if it's really worth mining. Well, how do we fill up those gaps in spatial extent? Well, different methods can be used, and one of them is called kriging. It's a statistical interpolation method to mathematically predict the value of your missing data using weighted averages of known values in the neighborhood using one of several ways. One is a variogram, where we look at the difference between two values at two locations, or a semi-variogram, where half of the average squared difference between values at two locations at the same distance apart. It's interesting, it's named for a person, a pioneer in distance-weighted averages. R software is often mentioned as one way you can do statistical analysis. R is an open software, source software that includes tools that can perform classical and modern statistical techniques and help you with your data analysis and display. It can store your data and help you manipulate it. It uses programming languages, syntax and semantic languages, and can be extended using packages that work well with it. Users can also customize those functions. In order to use it successfully, though, you really do have to have some understanding of coding and mathematical operations, including matrices. There's a good introduction to R at this link below. Here's some helpful links that you may want to look at. One is just you looking at mathematical symbols so that you can see what those equations and all the items within them really mean. There's also a good dictionary of terms at esri.com, more on Moran's, and ArcPro help for other statistical packages. See the Geotech Center website, that's geotechcenter.org, and there are additional concept review modules. If you really need more in-depth information, there were the links that I showed you, but there's also model courses on topics that may help reinforce your knowledge in geospatial technology. Thank you so much. I'm Ann Johnson. Please do contact me if you have any suggestions or questions about this module.